Hello there. Welcome to the second session of your first week. What we will do in this session is to revisit the simplified problem, review the solution again, and mainly to offer arguments about correctness. This is what we will see mainly in this session. We will also see an implementation, particularly based on spreadsheets. We will examine the generalizations of the problem and discuss the data structures and the processing involved. Professor Sani has discussed the simplified version of this problem where 2 or maybe 3 roommates were considered. We will denote the number of roommates by n roommates. We have seen this before. K events will denote the event. Each event will be denoted by an event ID. Some roommate will be denoted by a roommate ID. At the end of the month, we will represent an event by rows and each roommate by a column. Therefore, at the end of the month, we will have a set of rows denoting the various events that have been shared by the roommates, and along each column will be the expense or the money that has been contributed by one roommate for a given event. This two-dimensional array or matrix can be represented as expenses for an event ID by a roommate J, whatever may be the expense. For every row, we wish to share the expense amongst all the roommates, that is columns. This can be done by subtracting the per head share for each roommate from every roommate's current state of affairs. Roommates with negative numbers will be the ones who will have to pay, while roommates with positive numbers against their names will be the ones who will receive money. At the end of the month, we simply add the columns. Again, the negative ones will have to pay and the positive ones will be the receiving money. Let's look at the correctness of this approach. What do we really mean by correctness? What is it that we want? Here are some questions whose answers would be very important to us. After all, we are making a machine do these things, not another human being. Why is the subtraction of per head expenses for each activity fair for all roommates? Why are the end of the month column wise totals also fair? How will this notion of fairness change as we add complexity to the problem? After all, we are considering a simplified version of the problem. But it's a good idea to have this thought in our mind as our complexity gets added. In what other ways can thinking about correctness be useful to us? There could be other questions, but for our purposes, these are key questions for us. Let's take them one by one. What do we require out of the idea of correctness, the fairness approach? Well, everyone who contributes more than his or her share must be returned exactly that excess contribution. Similarly, anyone who has not contributed must eventually pay exactly that same amount, whatever they owe. In fact, more strongly, no more, no less. No one receives more than whatever is the share that he or she is entitled to, and no one pays more than whatever he or she is required to. This notion of fairness, you only pay as much as you owe and you only receive as much as you have contributed. Let's look at how this idea of fairness actually works out given our solution approach. Suppose, for example, let's start with the first event so that there are no expenses or payments to be settled or reconciled. Suppose a roommate pays for an event some amount X. Then given that there are n roommates, the per head contribution is X divided by the number of roommates. Let's call this per head contribution as P. Our approach says that we subtract P from each roommate's contribution, which currently is 0 because it is the first event. The balance amounts then would be, for the roommate who has contributed, it would be X minus P. X has been contributed by that roommate and P is his or her share. Therefore, the extra amount is X minus P. And since it is subtraction of P from 0, for the other roommates who have not contributed, we will see minus P. This is quite consistent with our idea that roommates with negative numbers against them would have to pay, and roommates with positive numbers against them would have to get paid. It's a simple algebra to see that the sum of X minus P of the contributing roommate and the minus P of the rest of the roommates is 0. Let's look at the end of the month's totals. Why are the end of the month totals also fair? The column-wise amount represents a single roommate's contributions or per head shares owed to others over all events in that month. Adding all the amounts of for a column gives the net amount that the roommate must either pay or receive. If we consider the end of the month totals for each roommate, and given that the amount to be paid are negative and amounts to receive are positive, then you can use laws like associativity or commutativity of numbers for the addition operation to show that the total column-wise sums must always be 0. Let's go to the next step. How will this fairness change with complexity? Recall that we have two distinct directions in which we can add complexity in this problem. One is the problem itself can be made more and more general. Why should we wait at the end of the month for the totals? Why should we always have totals for everyone? Maybe as a roommate, I might just want my total for that point of time. There could be far more roommates than what we have just considered. And so many other ways. We have already seen that. The second way would be the generalizing the computer-based solution. We would like to think whether as we add any kind of a complexity, will our solution approach still remain fair? In fact, it will. The argument that the sum of the positive excesses and the negative debts must be 0 will always be true. This is the unchanging behavior or invariant of this problem. In fact, this invariant ensures that the solution is always fair and hence correct irrespective of the additional complexity. Finally, let's look at in what other ways can this thinking about correctness help us. Say if we have millions of roommates, although it's quite unlikely, but suppose we have millions of roommates with millions of events. This invariant will still guarantee the correctness of our solution. In fact, it can help us identify some implementation errors. For example, our machines are typically finite precision machines. Therefore, overflows and underflows can occur. If we think about it a bit, then any such overflow or underflow errors will immediately reflect in our invariant becoming non-zero, that is false. The moment we see that our invariant is non-zero, we know something has gone wrong. This is a good time to take a pause and think about the issues that we have just discussed. We will demonstrate the solution using a spreadsheet. On your screens, you will see slides which show a LibreOffice 6.0 spreadsheet, a snapshot of that. We have a column event ID. This means that each row represents an event. We have a column which captures the expenses for that event. We have a bunch of columns for roommate IDs. We have shown 5 roommates here, who are F1, F2, F3, F4 and F5. In practice, these could be some real names: Ramesh, Sudha, Nikhil, whosoever they may be. We have also illustrated that roommate F1 has paid some amount for the event with event ID 1. This region over here denotes the input data, that is, for an event, how much has been paid by whom. This region denotes the calculations and the output results. This is where we calculate the fair share of each roommate for every event, and we go on accumulating the fair shares for all the events. Notice the last column. The last column is the invariant. It is the sum of each row of the calculated part, which is the per head share. We have already seen that this is an argument for correctness. So in the spreadsheet, we have just summed the rows and we write that in this particular column. If that is 0, then we know that our calculations have been correct. Here is also a spreadsheet formula for people who might not know about spreadsheets. This formula calculates the sum of contents of cells starting from column J and row 13 to column N and row 13. In this particular example, we have 55 minus 45 plus 55 minus 70 plus 5, which is 0. Also, incidentally, this particular row is the end of the month row, and as we have already seen, is an invariant. It is 0. Therefore, our spreadsheet solution is correct. It exactly balances the amount that is to be given and the amount that is to be received. Let's have a look at an actual working solution. Here is an Excel spreadsheet of the same solution that we have seen. Let us add a 7th event. Let's say that it is rupees 200. This means that amongst 5 friends, the per head contribution is rupees 40. Let's assume that friend number 1 pays 20 rupees, pays all the amount 200, while others don't pay at all. Note that for friend 1, the excess amount is rupees 160. his or her share of rupees 40 has been subtracted from 200 and therefore 160 is the excess amount. Quite obviously, the others have to pay rupees 40 each. There are 4 of them, therefore 160 rupees totally have to be paid by the other 4, and our friend who has contributed must receive 160 rupees. The invariant is therefore 0. This is again a good point to pause and review what has been done. Let us now look at a few data structures of this problem. The key data structure is of course a table. In our discussion, we have called this as the expenses table, or it may be also referred to as a matrix. It would be good if we could index this table using the roommate ID. This could be done, for example, by using dictionaries in Python. We leave it normally with this solution. A program can be implemented in any language. For our course, we will be using Java. How to realize roommate ID based indexing, we leave it to you. The other pieces of information are really individual data types. For example, the roommate ID is a string. The event ID is a positive integer. The expense or per head share or such objects are real numbers, floating point numbers. We will also need the declaration of the method that calculates fair sharing. That's one important function processing to be done in this solution. Here is a declaration sketch of the method. Boolean compute per head share real expenses array. This is illustrative. This declaration is illustrative and uses a C++ Java style syntax. The method returns a boolean, job done or not. Maybe as we progress and add complexity, we might have to change the return type to a more suitable one. The method accepts one parameter, real expenses array, the table of expenses so far. Expenses are real numbers. We repeat, this is just a sketch of the essential data structures. Depending on the language that you use, you might have to define the correct way of you might have to use the correct ways of defining these data structures. Further, you may want to enrich these data structures. These are just bare bones sketch. For example, instead of pure numbers in the table, expenses table, you might also want to add date or location or description information. In our illustrations in the spreadsheet, we had shown one column, the date. That information was also captured there. You might also need additional methods. For example, it's possible that you might want to compute the fair share of a given roommate instead of all of them. So you might want to return an array of real numbers indicating the share of a given roommate given by roommate ID R, and of course our expenses array. This is a point where we will want to draw your attention. In some assignments, we may mandate the methods to be defined and used. Let me repeat that. In the upcoming assignments, for some assignments, we might state explicitly that which are the methods that you need to define and use. Whenever such a mandate is given, then your solution must be constructed using the stated methods and any other methods that you may need, but stated methods are required. If they do not exist in your solution, we will not be able to evaluate it, and therefore you will not earn credits for that effort. As we come to the end of this session, let me sketch our path to the web app. We will shortly look at the command line version of the program. The command line version is going to be a single user, a single CPU that is shared amongst individual roommates. There will be single localized information base. There is no network. Essentially, this is a very monolithic architecture. We would generalize by incorporating multiple users, but still with a shared CPU. That shared CPU is what we would call as a service access point. This would involve including extra piece of functionality like user authentication, and we might have to think about information separation versus sharing. We will look into these as the course progresses. Next, we will introduce the network, but the main idea of the network is that it's a separator of input and output and the processing. The web is we will look at the web as a technique of network-wide input and output. It opens up the possibilities of multi-access point architecture. Therefore, our architecture will no longer be monolithic and will be distributed. Our next generalizations would be along making our app multi-user with multiple access points, with multiple groups of roommates, and so on. You can use this preview to start thinking about how to generalize your app in various ways. Towards the end of this course, you will have a 2-week project where you can generalize in as many different ways as you can think. Of course, you will be required to commit your generalization first. You have to state what is the generalization that you are going to do and only submit that part. This is a good point again to pause. With that, we come to the end of the second session of week 1. Thank you. See you in the next session.